Hi everybody. This lecture I'm going to be doing hopefully two different things. First talk about limits, but then I'm going to treat the limit stuff a little bit short, and then we'll push on and do actual derivatives. These are for functions of multiple variables. So the limit stuff first, that's section 15.2, which is titled Limits and Continuity. Well, okay, I'm going to abbreviate continuity. Let me first recall to your mind something from Calc 1 when you were doing limits there. If you said something like the limit as x approaches some value a of a function f of x, do you recall that this existed provided you could talk about the limit from above and below? That is, this limit exists. Actually, it's an if and only if connection. The limit as x goes to a from above of f of x, and the limit, this one over here. Okay, it's a funky looking limb, but I'm not going to fix it. Limit as x goes to a from below of f of x. If those both exist and if they're equal, that's what you needed to know that the limit, just without any decorations on it, exists. And you should think about this as saying you're on some graph. Here's the point on the x-axis that's labeled A. You ought to get the same value as you approach A from the left. Sorry, that was the right, as you do if you approach it from the left. If that's not the case, actually what happens is there's a discontinuity. Maybe from the right it's higher than it is from the left. But then you can't say the limit just, the unvarnished limit that just is independent of path exists. Maybe I should make sure to draw you the other option, right? You could have, here's the point A on the x-axis. You could have something from the left, it looks like this, and then from the right, it looks like this. Maybe the function's not really defined at A at all, but this is really quite bad because from one side it looks like the limit is one thing, from the other side it looks like another. Well, so I'm going to try to illustrate for you how this all plays out when you've got a function of two variables with this tortilla. If the tortilla was as is, and maybe I can prop it up with some random objects so it looks like it's a function, right? There's some, it's not just flat. I mean, actually a flat tortilla would be a function too, but if it was like this, then I could talk about the limit as I approach some. See this brown spot right here? Let's mark it so it's a little bit clearer. That spot, I could say that's a spot on the tortilla above a particular point in the xy plane. And if I approach along the surface of the tortilla from any direction, it doesn't matter. I'm going to arrive at that same z height, right? But there's more options for a tortilla. Let's put a slice in the tortilla. Now, I could make a function, and there are definitely functions that exist like this, where the value at the limiting point, at this point we're trying to approach, well, I mean, the value of that point probably is the one that's marked above. It depends whether you consider this slit to be a place where the function is defined or not. And just like with functions of one variable, you can sometimes make a choice. We could say it's defined along this upper part of the separation, and those points are not included in the graph down below. But anyway, limits don't really care about what the value is at the point. Limits are all about how does it look as you approach the point. And if I approach this guy from this side, or On this side, actually you can follow any kind of curve to the point, but I get different numbers, right? The heights of those positions, because of this discontinuity in the surface, are different. So this is a case where the limit of the function of two variables as your xy point approaches a particular location in the xy plane via any route, they don't agree with each other, and so you can't talk about a limit there. Ruined a perfectly good tortilla. Okay. Well, because of what I just showed you with the tortilla, we need a better way to express when a limit is, well, when it exists and what its value is. And the version of this that appears in the book, I think, emphasizes things a little bit, well, I don't prefer the way they emphasize it anyway. So let me give you a variant of it. It's really the same definition, just sort of rephrased a little bit. So we're trying to define the idea of the limit as a point in the xy plane approaches a fixed point in the xy plane. So think of x and y as actual variables. A and b are constants, though. They're particular numbers. But the idea is the limiting value of this function of x and y as we approach a, b should be L. That's the thing we want to define. This is an example of what's known as an epsilon delta argument or definition, because, well, those are the letters that are traditionally used in it. So this funky little guy here is an epsilon. It's a Greek letter for E. If you on campus, we have an honor society that's called Pi Mu Epsilon. So they use the capital letters for that. Pi and mu are P, well, the Greek P and M, and then epsilon is a capital E, I think, P and E. But if you rendered this in lowercase, it would be pi, mu, and epsilon, like that. Anyway, epsilon. And then this guy looks like a D, that's delta. I'm just going to make my pretty version of this definition a little bit ugly by inserting those in there. Maybe I should just get them out. That was only for your information, what the letters are. Let's not confuse the issue. So what is the issue? Epsilon here is going to give us a sort of a vertical tolerance, that if, I like the word tolerance here, if you're within epsilon of the actual limiting value, that means in a sense you're close to the limit. And delta is going to give us a horizontal, although horizontal now means in a plane tolerance as well. So what's the idea? Any vertical tolerance that you name, any small positive number epsilon, for any such thing, it's possible to find a delta, a tolerance in the xy plane, such that, this is where I differ from the book. What I want to say is, if the distance of our point xy from AB is small, less than delta, then the distance of f of xy and L is also small. So if you tell me how close you would like to get to the value of L, I'll need to come up with this delta and say, well, bring your point xy that close to AB, and you'll be in that range. So the best way to phrase this, probably, if you're speaking it, would be to take this sentence and and replace it in English language with something like xy is close to AB. And this sentence about the distance between the functional value and L, you could translate that into f of xy is close to L. So that, if you reread all this with replacing the equation or the math stuff with just the idea of closeness, I think it helps. The only extra piece here is it's not just a random sense of closeness. XY is close in that it's within delta. Maybe I could put in that. Close within delta of, I can't fit it, darn it. All right, I just got to write bigger. Close to, within delta of. Anyway, if the point in motion is close within a circle of radius delta to the point AB, then this one should be the functional value at xy is close to L. And again, the thing that we've got there in the inequality tells you how close. It's a little more precise than merely just saying close. You might say xy is delta close to AB, but I think that's a strange phrasing. F of xy is going to be epsilon close. All right, fine, I'll go with it. Epsilon close to L. Maybe that works. Okay, so now let's give the version of this that appears in our textbook. First off, they use the phrasing of this if-then relationship in reverse, which I always hate. They say distance of f of xy from L is less than epsilon whenever the distance of AB and xy is less than delta, which I suppose that's okay, but it sort of it tends to make people not recognize that this is an implication, an if-then direction. A directed if-then sentence. All right, so let me erase and I will put the book's version of these things on the screen. Okay, so here it is, as more or less as it appears in the book. I still left a few nuggets out, but I wanted to get the main points here first. So again, we're talking about figuring out the limit as a moving point in the xy plane approaches a particular point in the xy plane of the function evaluated at that point that's in motion. And if this limit exists and it's equal to L, well, this is the definition of when such a thing happens. So that it's equal to L if the start of this is the same. Given any epsilon, there is a delta such that, and both of these need to be positive numbers because they're interpreted as distances. But definitely think of them as being tiny. Often you think of epsilon as being tiny and delta is even tinier. You have to really, you have some conditions on delta. Well, other than the change in order and using the word whenever, this is the same as what I wrote before, except that I've included what the senses of distances are. So you see this square root of x minus a squared plus y minus b squared? That's how you define the distance between 2 points in the xy plane. So this is still saying the distance between xy and AB. It's just written out into algebra. The z coordinate, or the output of these functions, and the number L, those are just single numbers. So how do we talk about the distance on a one-dimensional axis? I mean, you really could think of this as z. It's just the absolute value of the difference. So both of these things, while they look different, they're just how to get distance in the context you're dealing with. If you've got single numbers, you subtract them and then take the absolute value because distance should be positive. If you've got points, then you have to do the Euclidean distance, that distance formula thing. So the value of the function will be very close to L. It'll in fact be within epsilon of L every single time you've got your point xy rather close to AB, within delta of it. Okay, so the remainder of this section on limits is developing some rules, how to work with limits. some of which are just completely obvious, and others are a little bit tricky. But they all are just like the ones you dealt with in Cal 1. And in the real process of finding the derivatives of things, we actually very seldom have to go back and use the limit definition of the derivative. I mean, I'm going to define the derivative in terms of limits and everything, but there's other ways to approach it. So I'm going to give this whole section on limits a little bit of a short shrift here, and we're going to press on to talk about derivatives. Well, we're not going to get the full story about derivatives right away, but we're going to get what are called partial derivatives first. Partial derivatives are what it sounds like. They're part of the answer to figuring out the actual derivative. And so I want to try to sketch for you the generic situation. Here's the xy plane. That's the x coordinate. Here's the y coordinate. We're going to be, and this is a flat plane, so you can think of it as having a grid work of these lines in the y direction, these lines in the x direction. Right? Above this plane, we're going to imagine a surface. So z is equal to a function of x and y. And I don't mean to be specific, right? I don't want to talk about a particular z. So just generically, there's some surface up here. Now, I want to make what I usually call a magic carpet picture for you, which is you just lift the corners of this flat plane up somewhere randomly in space. There. And then you try to connect everything together with sort of images of these vertical and horizontal lines that are in there. You might have something like this, and then that, right? And the idea is that each one of these lines could be projected up onto this surface. I don't know how they'll look exactly, but maybe something like this. Does that give you the sense of a curved surface sitting up above the flat xy plane? That's the hope. Okay, so what we're going to do for partial derivatives is think about changing our location. You might be at a point here whose coordinates are AB, and that corresponds to, looks like it's a little bit off, but it corresponds to that point, its height. The height of that point is z of AB. What I want to do is think about moving strictly in the x direction from there. What if I go sideways? This might be, what is the x coordinate of that point? It's A. What is the y coordinate of that point? It's B. So what if I just held y fixed and let x change and we moved this way? That would correspond up here on this magic carpet to moving along this line. And the beauty of thinking of it that way is I've just turned this into Calc 1. I've just turned the question into something that we did previously. So this line is where y is equal to b. And I can get you the derivative of this. I can get you the derivative of this motion because the thing changing here is just x. The y coordinate is b. So what we're doing is, let's write it as we would with limits, the definition of the derivative. The limit is h goes to 0. The function looks like f of x comma b. And we will subtract the value at AB. That's where x is equal to A. And well, y is always going to be b on this one. And you divide that by h. This is the difference quotient. This just looks like f of x minus f of a, except for those b's on there. But because we're keeping y fixed, that really is a function of just a single variable. We've created a function of a single variable out of our function of two variables by nailing down one direction. The y coordinates aren't going to change on us. So that's a derivative of a sense, or at least it's part of the story of the derivative. And this is called the partial derivative with respect to x. We're letting x change, so that's the thing that we're changing. Now, there are two notations for this. Leibniz style notation looks like this: partial f partial x. They use slightly, remember seeing this kind of notation before. It looked like df over dx. These are different symbols, and they're not even deltas. Those are called the partial derivative symbol, but they're supposed to look a little bit like a d. They're just there to remind you this isn't the ordinary derivative. This is just a part of the derivative of the surface. So partial f partial x is that limit. The Newton style, or something that's, Newton didn't do this, but it's more in keeping with the notation that he did, would call this the derivative with respect to x by putting a little subscript x on it. So f sub x, partial f partial x. Both of these actually are evaluated somewhere. These are actually functions, and they depend, in fact, they're functions of two variables. They depend on where you're doing. So if we were at the, if we're at the point AB, we would need to write actually partial f partial x evaluated at AB, and f sub x evaluated at AB. Another notation for this is maybe too much notation, but what you got to be able to spot this stuff when it appears to you, is something a little bit akin to what we do when we evaluate an integral, when you have that vertical line with the upper limits and the lower limits. You could also write this: partial f partial x evaluated at AB. That's what that vertical line means, and I don't have enough room for this, but you could do a similar thing with f sub x, vertical line, and AB written small down below. All right, maybe I can fit it right in here. But now it's running into that junk. I'm sorry. Yeah. So let's do a quick example of this in practice. So here's a function. Z is x squared cos y. So the function is x squared cos y. I'm setting it equal to z, so we think about that as a surface, where the z coordinate is a function of where you are in the xy plane. I have no idea what it looks like. Well, I have some idea what it looks like, but its actual appearance isn't necessary. So I could try to sketch this, but we don't need that to take the derivative. Suppose we want to find z sub x evaluated at about 1 pi. Did I choose well? What's the cosine of pi? Is that -1? Yeah, okay. So z sub x evaluated at 1 pi, well, let's write out that limit that I just had a second ago. It'll be the limit as h goes to 0. The function is always going to be evaluated for its y coordinate at pi. So we're going to have, we're going to have x plus h squared times the cosine of pi minus x squared times the cosine of pi all over h. That's what that limit we just wrote says if you substitute in the jump that the particular function we're dealing with. But look, cosine of pi is always just the number -1. So what we've got here is, in fact, if there's a -1 in both terms, I could factor that on out, and it's a constant. I can pull it right on out of the limit. It's -1 times the limit as h goes to 0 of x plus h squared minus x squared all over h. I think you should recognize this. Do you recognize this? you should have, it's from 2 years ago, or 2 semesters ago anyway, but this is the limit you use to evaluate the derivative of x squared. And it ends up being 2x. I guess there's a minus sign on it, but you just take the derivative. This literally is 2x, which, you know what the derivative of x squared is, so that's not unfair. So if you look at this sort of overall, rather than going through the limit process, look what happened. We took z sub x, and we're doing it at the point 1 comma pi. It's just figure out the derivative of that guy, 2x. Actually, let me say it in stages here. Take the derivative of x squared, the old-fashioned way, then leave cosine y alone, and then evaluate at x is equal to 1 and y is equal to pi. In other words, go ahead and differentiate x squared, you get 2x, leave cosine y alone, and then stick your numbers in. Which is, the number was 1, that'll be a 2, and pi, that'll be a minus 1. So minus 2. Well, that whole business with limits actually turned out to be unnecessary if we know how to take the derivative of these things separately. And we kind of do. Mostly we do. So partial derivative, the nice way to say partial derivative is this. Treat the other variable as if it was a constant. Cosine y is not changing because y is set equal to pi in this. And so cosine y can be thought of as a constant, which means you can pull it out of the differentiation process. Yeah, that's really the mantra you should be saying to yourself when you're taking partial derivatives. Treat the variable that's not changing as a constant. Running out of space. So let's do another example. Just using this mantra for us. Suppose I had z is equal to x squared, y squared. Product of x squared and y squared. The x partial derivative of that is, pretend y squared is a constant. Then it's just a constant multiple of x squared here. I happen to be writing it on the right rather than on the left, but if y is a constant, y squared is a constant. And x squared, take its derivative. You get 2x y squared. Now, so far I didn't tell you anything about the other partial derivative, but we can now do that very easily. What's the y derivative? Well, that's where you're going to treat the other variable, which will be x in this case, as a constant. So that x is fixed, that means x squared is fixed. This thing in front is just a multiplier. You just bring constant multiples along for the ride, but you do have to differentiate y. Sorry, you do have to differentiate y squared, and you get 2y. And you should notice, by the way, these are not the same. Zx and zy, actually, we shouldn't imagine that they are the same. Geometrically, what these guys give us is how is the ground sloped if we move in the x direction versus how is the ground sloped if we move in the y direction. And those can be quite different. Well, just like in Calc 1, once you have the process of differentiation, you can think about doing it multiple times. So you can take the partial derivative with respect to x twice, for instance. The notations for that are, these are called how do we say this? Higher order partials. The notations are different again, but you could think about f sub x, and then we'll take the x derivative of that. But nobody bothers to write it like that because it's easier to just say f sub xx. Take two derivatives with respect to x. That's rather like the double prime. So that's the Newton style notation. Do you remember the mix-up with Leibniz notation that like the second derivatives, the exponents go in funny places? It sticks around when we do partials. So we should have partial squared of f over partial x squared. That's the same thing really as f sub xx, and both of these things become functions of two variables again, so that actually is why we're allowed to do this operation a second time. We can think about it. Well, let me do one for you. Suppose we did z is equal to, how about x cubed times sine x, sine y, sorry, the second variable to be in there. When I take the derivative with respect to x, I pretend y is a constant. Y is a constant, then its sine is a constant. So that whole thing is just some number. So z sub x would be 3x squared times that number. I mean, sine y. In other words, functions, things that are strictly functions of the other variable just get pulled down. They don't change. Things that are function of the variable that we're imagining changing, we take the derivatives of those. If I wanted z sub double x, then I've got, again, a constant in terms, this piece is just fixed, and if y is fixed, but the derivative of 3x squared becomes 6x. And there's a tendency of an error people make is to not bring this along because you go, oh, the derivative of a constant, it's 0. But that would mean the whole thing was 0, and that's not what we're after. We're not taking the derivative of this thing. We're treating it as if it was just a number, and so it's a constant multiple of something that's got a variable in it that we're actually differentiating with respect to. I could actually do this one more time. You could have z sub xxx, which would be 6 times sine y. And now, if you want to go nuts, you could do a fourth derivative. Well, what's going to happen with that? Now I've got a constant times, not really a constant, but we're treating it as one. So you get 0. The fourth derivative here is 0. Truly 0. Not 0 times, well, I guess you could say it's 0 times sine y, but that is 0 after all. This notation is actually easier to deal with than the Leibniz notation in this case, but this other notation does have its place. In certain ways it helps us. It's time to mention something that's a little strange, and it's hard to physically interpret, because these higher order derivatives, when I just am doing them with respect to x, it's just I'm thinking about the 1D curve that I get by leaving y coordinates fixed and moving strictly in the x direction. You get the idea? I'm trying to mime this for you. We've got a surface z of xy out here, and I'm just moving along in the x direction. So I'm getting an ordinary two-dimensional function. Y equals, you could think of it as y equals f of x, although it's really, I guess, z equals f of x. But this is ordinary calculus on that one-dimensional thing. When I take the x partial, again, I get a function of two variables, so I can do partial derivatives on that thing. What's to prevent me from doing f's x derivative and then taking the y partial of that? And it's really quite a good question. What would that mean? What it means, I think we'll leave for later, but can we do it? Absolutely. It's actually pretty easy to do. In fact, like the change of notation here, we don't have to specify stuff like that. Just keep the variables in the correct order. F sub x, y. That means take the x partial first and then take the y partial of that. Sure, let's do one of those. I think I like that, the example I did a little while ago where f of xy is x squared y squared. What's f sub x? It's actually a function of x and y too, so let's not forget that. It is 2x times y squared, because you take the derivative of this, you treat that as a constant. Now what if I take the derivative of that with respect to y? That's how I would get f sub xy, which again will be a function of both variables. Well, I'm just going to look at this expression and play the same game, but y is the variable and x is treated as a constant. All right, so I get 2x, 2y. Or, I guess we should simplify it, 4xy. Perfectly easy to do. There's a kind of a funny business going on here that I want to point out to you. What if we did this kind of in the other order? If I figured out what f sub y was first, what's f sub y? Starting with this f, well, it's x squared times 2y, or 2x squared y. And now what if we took the x derivative of this? We'd get f sub yx. Again, it's a function of two variables. And what we're doing, we're taking the x derivative of the guy I've got above here. That's going to be 2x, and the constants will all come along for the ride. So we get 4xy again. Notice that these came out the same. Is that necessarily the case? These kind of derivatives where one's with respect to x and one's with respect to y, those guys are known as mixed partials. So, just terminology here. What I'm asking is, do the mixed partials have to be equal to one another? There's two options for how I could take this derivative, these derivatives. One is differentiate first with respect to x and then differentiate with respect to y. The other is do the y derivative first and then the x. There's no reason a priori that those should come out the same, but they seem to have in this case. Well, that's actually a result that's known. It's called Clairaut's theorem, that mixed partials are equal. I want to watch out. There's probably a we need the mixed partial to be continuous throughout the domain of the function. But other than that, Clairaut's theorem can be stated in more generality, but basically it's that f sub xy is equal to f sub yx, and then you can go beyond that. For instance, I could do two x's and then a y, or I could do an xyx or a yxx. There's lots of ways where I could have two x derivatives and one y derivative. Three different ways you could do it with a third order mixed partial. All right, so that should get us to the point where you can take your partial derivatives. There's a little piece of section 15.3 that I want to finish up, but that'll be for next time. So have a great weekend. This will be posted sometime on Thursday. I should have it up actually mid-afternoon Thursday. Ciao.